Hello students, welcome to Shri classes. Lecture number 4 will continue with magnetic effects of electric current. Two important concepts that we are learning today are force on a current carrying conductor in a magnetic field, and the direction of the force experienced by a current carrying conductor is identified by Fleming's left hand rule that we are going to study, and electric motor, which is on the above principle. So see here, in the Oersted experiment we saw a current carrying conductor produces a magnetic field. So if we keep that current carrying conductor in one more magnetic field, then it will experience a force and thereby the deflection, and that is what we are going to study now. See, force on a current carrying conductor in a magnetic field. Important here is there is a horseshoe magnet, and in which this conductor is placed. In which direction, in which orientation this conductor is placed, we'll study in detail. Thing is, if this conductor is placed inside this horseshoe magnet and if a current is passed through this one, then this conductor behaves like a magnet. It produces magnetic field. That magnetic field produces a force on this magnet, outside magnet. Thing is, French scientist Henri Ampere, he said that the outside magnet must also exert equal and opposite force on the current carrying conductor. Do you understand here? See, the direction of magnetic how this conductor is placed, I just want to explain to you. This is how the conductor, assume that this is a conductor and this is a horseshoe magnet, north, south. This is how the conductor is placed. I hope you are able to see this. You got it? This is how the conductor is placed. This is how. And this is the diagram. The diagram is something like this. North is down here, and therefore something like this. Yeah, exactly. Or north, I can't have this way. Okay, no problem. It is something like this, but this is north here, it is south, I have mentioned. It's okay. This is how the conductor is placed. You got it? This is how the conductor is placed. I hope you are able to understand the placement of the conductor. Now, when this conductor is placed like this, see, this gives the direction of the current. If this conductor is placed like this, okay, what happens is either this conductor may move this side or it may move outside. So this is how this conductor will experience a force. See, if this is a conductor, when a current is passed through this, it behaves like a magnet and it produces magnetic field lines. This magnetic field exerts a force on this magnet, okay. And what is that thing is, Henri Ampere said, when this conductor exerts a force on this magnet, equal and opposite force is also exerted by the horseshoe magnet on this conductor. Horseshoe magnet can be kept stationary. In that case, this conductor will experience a force and a motion, displacement, and therefore this is loosely connected in the sense loosely placed inside, and therefore the force experienced by this conductor can displace this conductor either this way or this way, which can be determined by Fleming's left hand rule. That is what we are going to study here. So couple of points, let me read over here, and then I will proceed to the board. We'll discuss these entire aspects on the board, and then we'll see. A current carrying conductor produces a magnetic field. Yes, we know by Oersted's experiment. This field exerts a force on magnet placed in the vicinity of the conductor. Here this is a conductor. When current is passed through, it produces a magnetic field, and that magnetic field exerts a force on this magnet. And French scientist Henri Ampere suggested that equal and opposite force is exerted by this magnet on this. Now this conductor being held loosely, the force exerted by the horseshoe magnet on this will displace this conductor, and hence we can find that this conductor undergoes the displacement, that is force and thereby the displacement. And the direction of this displacement, either this way or this way, can be identified by the Fleming's left hand rule. Here, according to your textbook, AB, I'll read it here. Thus a current carrying conductor placed in the magnetic field experiences a force and thereby the displacement, that is motion, and magnitude we'll see. Here this is AB is an aluminum rod. Construction we'll see how it is done. Horseshoe magnet, aluminum rod. It is suspended through this stand inside this magnet. End terminals, like this end and this end, is connected to the battery terminals or here. This is a positive terminal. This end B is connected to the positive terminal, and this end is connected to the negative terminal, and K is a switch. The moment you switch on, it will get displacement, and this is the entire experimental setup. This I'll explain it on the board, and then we'll see, we'll again get back to the PPT. Okay, here in the textbook it is given aluminum rod of AB, aluminum rod AB of about 5 cm in length. The length of the aluminum rod is about 5 cm. You can take copper rod and all, but definitely not steel rod or magnetic materials. You cannot take it because it will get attracted. So the conductors are electrically good conductors, but not magnetic conductors or magnetic substances. We cannot take the magnetic substances. We'll see the magnitude and all, how it depends upon. Let me explain to you on the board first. Okay. Yes. Here a drawing which shows a horseshoe magnet. This is a conductor. It can be an aluminum or copper, which is connected to the battery terminals, and there is a switch. K is the switch. Similar arrangement I have done once again here. Here it is this end, if I mark it as A and B, this is also A and B here. Here this A terminal is connected to a positive terminal, and here B is connected to the negative terminal. So I will mention here A, B is negative. In this case, this is negative terminal and this is positive terminal. As I said, whenever the current passes through this conductor, it produces magnetic field and it exerts a force on this stationary horseshoe magnet. Equal and opposite force is exerted by the horseshoe magnet on this conductor, because two magnets, when they come into each other in closer vicinity, you can find either the repulsion force or the attraction force, isn't it? So here what happens is, whenever equal and opposite force is exerted by this magnet on this conductor, and therefore this conductor AB being suspended freely, it can displace. Because of the force, it can undergo a displacement. So in which direction displacement it undergoes displacement, we'll see that. Before that, see here the directions, I'll mark it. The direction of the magnetic field is from north to south. You know, externally the direction of the magnetic field is from north to south. So magnetic field is from north to south. Conductor, let us see the current direction, positive to negative. That means from A to B. This is how the current is flowing in this conductor. And therefore, if I look at something like this, this is a conductor and this is placed something like this exactly. I hope you are able to understand. Now north south don't bother about. Here I have mentioned one polarity, but no need to bother about. You understand only the position of the conductor first of all. This is how the position of the conductor is placed. I hope you are able to understand this. Now the current is as shown in this direction, and the magnetic field is from bottom to top. In this case, this will experience a maximum force because the field is from north to south bottom here. If this is north to south, means from here to here the field, and the current is in this direction. So from here to here, the magnetic field is from top to bottom in this case, and direction of the current is perpendicular to the magnetic field. Magnetic field is this way, current is this way, and therefore magnetic field and the current are mutually perpendicular to each other. Only in this case the conductor experiences a maximum force and thereby the maximum displacement. That you should keep it in mind. So in case of maximum force and maximum displacement that is observed when the magnetic field and the current is perpendicular, in that case what is the magnitude of the force? Magnitude of the force is given by F equals LIB sine theta, lib sine theta. See, this is a horseshoe magnet here. If I place the conductor something like this is a horseshoe magnet, side north, south. If I place the conductor like this and connect it to the battery terminals, okay, here the magnetic field is from north to south, and if I connect this to something like this is plus minus, current is also in this direction I, and this is magnetic field B. Generally B is magnetic field. So magnetic field and I both are in the same direction. That means the angle is theta equals 0 here. In this case F equals L is the length of the conductor, I current passing through that magnitude of the current, into B, which is the magnetic field, into sine of theta is 0 here. Sine 0 degrees 0, and therefore force experienced by this conductor is 0. And hence we cannot place the conductor in line with or in the direction with the magnetic field lines. You understand? Because here what is this L is? L is the length of the conductor and I is magnitude of the current and B is magnetic field. Magnetic field. And theta is the angle between, theta is angle between magnetic field and current I. Magnetic field and current. If theta equals 0, theta will be 0 whenever the current is in the same direction of the magnetic field or opposite to that one. Whereas if I place this conductor like this or something like this, now north to south is this way and current is this way. Field and the current are mutually perpendicular to each other. In this case the conductor can experience maximum force, meaning if I place the conductor this way in this horseshoe magnet, it can experience the maximum force. And what is the maximum force experienced? Maximum force is given by, here once again I will draw that one. Suppose this is the horseshoe magnet. Okay, if I place the conductor something like this, then this is north and this is south. The field is in this direction and the current is in this direction. This is plus and minus. So theta equals 90 degrees and the force experienced by the current carrying conductor is LIB sine theta, which is LIB into sine of 90 degrees, which is Li into B. So maximum force experienced is length of the conductor into magnitude of the current into the magnetic field strength, which is measured in Tesla or Webers per square meter. So you understood here the force experienced by the current carrying conductor whenever it is placed inside the magnetic field is maximum, and it undergoes the maximum displacement when the current and the magnetic field are mutually perpendicular to each other. If both are in the same line, in that case theta will be 0 and the conductor will not experience any force. I hope up till now this you have understood very clearly. First of all, once again the magnitude of the force experienced by the conductor is given by lib sine theta. L is the length of this conductor, L. I is the magnitude of the current flowing through this one, and B is the magnetic field produced by this horseshoe magnet, which is from north to south, and that is the field strength which we are talking about. And theta is the angle between the magnetic field of the horseshoe magnet and the I current that flows through the conductor. If those two are mutually perpendicular to each other, only in that case the conductor AB experiences a maximum force and thereby the maximum displacement. If theta is 0, then force is 0. Please remember that, because I may use this principle in DC motor, in functioning of the DC motor, working principle of the DC motor. There probably I may discuss this F is equal to 0 in one particular arm of the armature coil. Okay. Now you have understood that a current carrying conductor, when placed in a magnetic field, experiences a force and thereby the displacement. How do you check the displacement, or in which direction the force is applied and in which direction the displacement takes place? For which we use the Fleming's left hand rule. Fleming's left hand rule. See, what is that Fleming's left hand rule talks about? Fleming's left hand rule gives us the direction of the force experienced by the conductor and thereby the direction of the motion of the conductor or the displacement of the conductor. Which, when it will give you, in which case it will give you? Only when the magnetic field and the current are mutually perpendicular to each other. Otherwise it will not give the direction of the force experienced by the conductor. Please remember that. So Fleming's law is applicable when the force experienced by the conductor is maximum. That is when the magnetic field and current through the conductor should be mutually perpendicular to each other. And therefore Fleming's law states that if we stretch our left hand's first three fingers, the thumb, forefinger and the middle finger, mutually perpendicular to each other. Look here, I'll explain. Here, Fleming's left hand rule. Left hand rule. What is that left hand rule? It is used to find out the direction of motion of the conductor when it is placed in a magnetic field. Direction of motion of the current carrying conductor when it is placed in a magnetic field. Direction of motion means it gives the direction of the force also. So what is that one? If we stretch the first three fingers of our left hand mutually perpendicular to each other like this, thumb, forefinger and middle finger, this is 90 degree, this is 90 degree and this is 90 degree. Yeah, this is 90 degree. This one, middle finger and this one. So we have to stretch our first three fingers mutually perpendicular to each other. Okay, mutually perpendicular to each other. In that case, I am marking some important thing here. See, in that case I am marking. Thumb indicates M, motion, M, and index finger gives me, or it should be pointed towards the field and motion field current. Middle finger should point towards the current. So you should remember MFC. I think it can be brought still closer also, no problem, so that they can understand in the beginning, because many students do not understand this concept at all. See here, I have stretched my fingers here, left hand first three fingers, thumb, index finger and middle finger. Okay, I am marking certain things. M for motion, so motion is due to force. So thumb indicates the direction of the motion of the conductor or the force experienced by the conductor. F indicates the direction of field. C indicates middle finger, direction of the current. Motion, thumb, field, index finger, current, middle finger. Motion, thumb, field, index finger, current, middle finger. So MFC. I hope you have understood. Now, in order to understand the what is that Fleming's left hand rule, let us see. What is the statement of the Fleming's left hand rule? when we stretch our first three fingers mutually perpendicular to each other, such that if the index finger points towards the field and the middle finger points towards the current, in that case the thumb gives you the direction of motion of the conductor. The thumb gives you the direction of displacement of the conductor. The thumb gives you the direction of force experienced by the conductor. Listen carefully. When we stretch our first three fingers mutually perpendicular to each other, such that if the index finger gives the direction, or if the index finger is pointed towards the direction of the magnetic field, and the middle finger, if it is pointed towards the direction of the current, in that case the thumb gives you the direction of force experienced by the conductor, and hence the direction of motion of the conductor. Let us apply this Fleming's left hand rule to this one. So I have made a small this thing also for your understanding. Here it is clear. Thumb here and index finger, or you can also say the forefinger, and this is the middle finger. So in order to apply Fleming's left hand rule, which is used to determine the force experienced by the conductor or the motion experienced by the conductor, we will apply this one over here. Now let's see here. This is a conductor which is placed in this magnet, already in this horseshoe magnet. Already you know the position of this conductor, how it is placed. It is placed like this. The conductor is placed like this. I hope you are able to understand. So here, north to south, the field direction. Field is index finger. So therefore I will point this index finger towards in the direction of the magnetic field. Current now, positive terminal and negative terminal. Let me switch on the battery. Let us switch on the battery. Now the current starts flowing. The moment current starts flowing, it experiences the force. Just a moment. Okay. So the current is from A to B. So what is that current here? A to B means, see, the middle finger is to be stretched along this one. Field I have to do as it is, but the middle finger, this is the middle finger, this is the field, this is the middle finger, is in the direction of from A to B it is. If that is the case, then the thumb is pointing towards you here, you can see this, the thumb is pointing towards you. That means this conductor moves out of the magnet, something like this. It moves out of the magnet. I hope you are able to understand. Once again, I'll use my three fingers. Let us point the forefinger in the direction of the field. This is from bottom to top. Yes, bottom to top. Turn your middle finger towards the direction of the current from A to B. Yes. So field is this way and this is this way. Field is upwards and this is upward, and my thumb is pointing towards you. That means this conductor comes out of the magnet, something like this. Out of the magnet like this. You got it? So index finger towards the direction of the magnetic field from bottom to top, and this middle finger from A to B. In that case, thumb gives you the direction of motion of this conductor, that is towards you. Clear now? Okay, fine. Come to this diagram. What is changed here? What is changed here is, let's see. The horseshoe magnet and the conductor is placed. Magnetic field is from bottom to top, north to south. Okay. Direction of the current here. This is A here, B here. From B to, like this the current flows. That means from here to here. I hope you are able to understand. From B to A here. Earlier it was from A to B. Now it is from B to A. Isn't it? Here also I will mark something like this. So here it is. Yeah. Let us switch on. Then only it is correct. Okay. Now here we will try to apply once again. Out of three fingers, the field and current are to be positioned. The field and current are to be positioned. If I position the field and current, the thumb should automatically give me the direction of motion of the conductor. Field, bottom to top. Yes, bottom to top. Current is the middle finger which is pointing towards you now, but I should align this from B to A. See here, this is how I'll align it now. Correct. This is how. In that case, the thumb is into the board now. Into the board. See here, this thumb is showing into the board. Field, current, thumb is into the board, and therefore the conductor, this conductor moves inside the magnet. Inside the magnet. That means, see, this is how it is. The conductor once can come out. I mean, if you something, the motions are. If this is a conductor, this is the conductor. Once this conductor will come out, once this conductor will move inside. These are the positions which I am talking about. Like this, once it comes, switch on, it will come and hold, stay there, switch off, go back, switch on, once again. Reverse the direction of the current, what happens? If you reverse the direction of the current, the motion of the conductor is in the opposite direction. In the beginning, if the conductor moves this way, then comes back, reverse the change the direction of the current, it goes back. So, by changing the direction of the current here and by applying the Fleming's left hand rule, we come to know that once the conductor moves out here and once the conductor is moving inside, that position I will mark now. In this case, the conductor is outside. It is moving outside. In this case, the conductor is moving inside. Is it right? Let me check once again. Field, current, the conductor is coming outside. Field, this index finger is the field. Current from B to A, change the middle finger. So, field, current, and the thumb is pointing inside. See here, thumb is pointing inside, and therefore this conductor moves inside. That's all about the Fleming's left hand rule. I think it is very clear, which I have understood. And very quickly, the magnitude of the force experienced is given by F equals lib sine theta. Theta is the angle between the current and the magnetic field, and L is the length of conductor, I is the magnitude of the current, and B is the magnitude of the magnetic field. Now let me discuss a couple of points which I have mentioned in my PPT. Okay, let me read out those things first. So I am reading certain points there from my PPT. A current carrying conductor, when placed in a magnetic field, experiences a force and thereby displacement. Yes, we understood. Magnitude of the force and displacement can be increased by, important point. What is that? How do you increase the magnitude of the force experienced by this conductor F and the displacement? How do you increase? That is the question. First, by increasing the current. Yes, by making, if you increase the magnitude of the current through this, it will increase. By increasing the magnetic field strength. B, by increasing the magnetic field strength. You understood? So, of course, by increasing the length of the conductor also, it is possible. Here, the length of the conductor again may increase the mass and all. So, there is a really restriction over the length of the conductor, and therefore, definitely F is proportional to all these three. But, for a given length of the conductor, if I talk about, for a given length of conductor, then the field can be increased, the force experienced by the conductor can be increased by increasing the magnitude of the current or by increasing the magnetic field strength. Is it clear? These are the two. And one more. Note, direction of force and hence motion can be reversed by reversing the direction of the current. Now, important thing here, one more point I will discuss, and then we will go to some couple of problems. Here, I reversed the direction of the current and checked that the direction of the force and thereby the direction of the displacement or motion changed. Similar thing can be experienced if the polarity of the horseshoe magnet is changed. For example, in this case, by applying Fleming's left hand rule, this is the force and this is the current, and therefore this thumb is making this conductor to move this side. Now let me change the polarity of the horseshoe magnet. This I'll make it south and this will make it north. In this case, the magnetic field is, in this case, let us apply the Fleming's left hand rule. Magnetic field is from north to south, from north to south. Current is from A to B. In that case, where the conductor displaces, let us see. Field is north to south, therefore tilt it, this forefinger. Current is from A to B, therefore tilt it. This is the middle finger. Current is from A to B. In that case, the thumb is pointing inwards, meaning this conductor is moving inwards. Earlier it was moving outward, now it is moving inwards, meaning the direction of motion can be reversed by two means. Either by changing the direction of the current in the conductor or by changing the polarity of the horseshoe magnet, and therefore we should be able to change the direction of motion, which is very clear now. Is it? Next. So how do you increase the magnitude of the force? By increasing the field strength of this horseshoe magnet or by increasing the magnitude of the current flowing through this one. That is for a given length of conductor. Okay. What else is there in this? I think let me check now first. Yes, we have a couple of numericals here. Now we'll look at, I think you can make a note of let me direct you to the PPT first and then you can make a note. Okay. So here, now almost camera can be focused to the entire thing here. Dear students, you can make a note of all these things, diagrams and all. So pause the video to make a note of this. Next slide talks about Fleming's left hand rule. It states that stretch the forefinger, middle finger of your left hand perpendicular to each other. Stretch the thumb, forefinger and middle finger of your left hand mutually perpendicular to each other. If the forefinger points towards the direction of the magnetic field and the middle finger points towards the direction of the current, then the thumb gives the direction of motion or force experienced by the conductor. And the magnitude of the force is given by lib sine theta, L length of the conductor, I current, B magnetic field strength. And theta is the angle between I and B, important. So these are the things which you can note down. Next, I have a problem here. You can pause the video and note it down probably. So see, there is one numerical over here. Before this numerical, I have to discuss a couple of points on the board first. So let me clear a part of the board also. Now, have you seen the arrow? Arrow is something like this. Oh, something like this. Or in a three-dimensional diagram, something like this. Something like this, pointer. Okay, and here in this case we have this is something like this, meaning at the back side you have a cross here at the back side and you have a pointer. This is exactly similar to the ballpoint pen which you can see here. if this point if the ball point is the arrowhead, if it is pointing towards you, then we see dot. There is one circle of this one, the circle over here, one circle and just dot. Okay, and if I see the back side, I see the cross. So if this arrow is shooted into the board, I see the back side and it looks like me, something like this. Generally it is, this cross is outlined with a circle, or even this is okay. This is what we can see, the cross here, the back side cross. If this is pointing towards you, and if this back side is inside, and if this arrow is pointing towards you, then we see the front face of the arrow as one dot here and one circle. Why I am talking about all this? Because this arrow is used to indicate, it is used to indicate magnetic field. Magnetic field direction. Okay, meaning here, if I consider something like this, if it is pointing towards you, that means the direction of the magnetic field is out of the board, pointing towards you. If you are reading a page, a textbook page, if this is something like this, then the magnetic field is out of the page towards us. If this is reversed, if you are seeing the back side, which is across here, then I say the magnetic field is into the board. While reading a textbook, if this is the case, then I say magnetic field is into the page, into the page. So with reference to your textbook or the examination question paper, if this is the pointer, that means the magnetic field is out of the, magnetic field is into the page. This is magnetic field is out of the page towards you. Magnetic field is into the page, away from you. Magnetic field towards you, out of the page towards you. Magnetic field into the page. Magnetic field out of the page. Magnetic field is into the page. This is towards you, this is away from you. Yes, students, this we have to understand. There is no other go. You must understand this. Whatever I said, you have to understand this now. So cross or dot is used to represent the magnetic field either into the board or out of the board. Based on this, this is out of the board towards you, this is into the board away from you. With respect to the page for textbook chapter also, you can see. Now whatever I write here, you have to note down, important. So far, a current carrying conductor produces a magnetic field, is what we have seen. How does the current flow into a conductor? Because of the flow of charges. Then can I say, if there is a flow of charges, then can current flow? Yes, current flows. Can it create a magnetic field? Yes, it can create a magnetic field also. And therefore, if I throw an electron this way, if I throw an electron this way, can it generate a magnetic field? Can it cause an electric current? Yes, it can cause. If an electron is ejected from left to right over here, then the direction of the current is opposite to the flow of electrons, opposite to the motion of electrons. This is the direction of current. Why it is so? See here, the current flows from positive terminal of the battery to the negative terminal externally, but the electrons move from negative terminal to the positive terminal, meaning conventionally the direction of electric current is opposite to the current direction of the electrons. That means if the electrons move from this way, current flows from this way, and therefore conventionally the direction of the current is opposite to the flow of electrons. First you should know. Next comes positively charged particles. So I talked about here an electron. Let me talk about P plus, protons. So if the protons are thrown this way, those are ejected in this way, what is the direction of the current in this case? It is the same as the motion of the protons. I is the direction, because here the electrons, if they are moving this way, I can say definitely protons are moving from positive terminal to the negative terminal, and therefore conventionally the direction of electric current is in the direction of the motion of positively charged particles, which are protons here. So electrons, protons we understood. One more thing, alpha particles. Alpha particles are doubly charged helium ions which are positive charges. Therefore I'll write here alpha particles are positively charged particles. Okay, and if the positively charged particles are ejected in one way, the direction of the, suppose those are thrown from left to right over here, the direction of the current is also same as the direction of motion of the alpha particles. Here this is the current. So the three cases you have to note down. If an electron is ejected or thrown or made to flow, then the direction of current is opposite to the motion of electrons. In case of positive charges, the direction of the current is in the same direction as the motion of the particles. I hope this you have understood very clearly. Okay, clear. Now with respect to these three, you note down in your notebook and the notes. We are going with respect to this concept, we are going to solve one numerical now. What is that numerical? Let us see. So let us see now, one numerical is there. An electron enters a magnetic field at right angles to it, as shown in the figure 13.14. The direction of force acting on the electron will be, that is the question asked. So let me draw the diagram here. This is example number 13.2. Magnetic field directions are given like this, and remember the parallel lines always indicate uniform magnetic field, and in this an electron is ejected this way. This is an electron. So an electron enters a magnetic field. This is the magnetic field and this is the electron. It is how it is entering. Okay, the direction of the force acting on the electron will be A, to the right, B, to the left, C, out of the page, and D, into the page. Into the page. We have to select this one. So, as I said, this is a magnetic field. Electron is ejected from top to bottom. Whenever the electron moves, the moving charges cause the flow of electric current, and moving charges produce magnetic field, and therefore the moving charge experiences a force and thereby the deflection, and the deflection need to be identified out of the four choices. How do you do this problem? How do you solve this problem? Fleming's left hand rule comes for the rescue. So let us try to apply the Fleming's left hand rule for this and select the right option. In order to apply the Fleming's left hand rule, magnetic field is directed from left to right. So forefinger, it is pointed here, forefinger. I think you can visualize forefinger in the direction of the magnetic field. Now I have to align the current finger. This forefinger gives the direction of the field, middle finger gives the direction of the current. Electron is from top to bottom, and therefore the current flows from bottom to top. So I'll say here this way, current. The current is top, means this is how it is. This way, field, this way, current. In that case, see here, the thumb is pointing into the board, Here, when I hold my textbook over here, I'll say into the page, and therefore the option D is the right one. Let me once again explain to you. These are the three fingers, MFC, motion, field, current. According to Fleming's left hand rule, if forefinger points towards the direction of the field and middle finger points towards the direction of the current, then the thumb gives you the direction of displacement of the conductor or the moving charges. In this case, magnetic field is from left to right, and therefore forefinger adjusted. Current is against the direction of motion of the electrons. Electron is introduced from top to bottom into the magnetic field, and therefore current is opposite from bottom to top, and therefore this is how I have to adjust, because this middle finger talks about the direction of the current. Field, current. In this case, the thumb which gives the direction of the deflection of the particle is into the board here, and therefore D is the correct option. Let us check that one. Yes, answer is option D. That is how it is. Okay. Now what I will do is I'll change the direction of the motion of the electron, and let us see what happens. Let me change the direction of here. The electron is ejected in this way. So in this case, what is the direction? What is the direction of the electron? See, this electron is here. It is the electron, and this is ejected this way. What about the direction of the current in this case? As the electron flows from bottom to top, the direction is from top to bottom, opposite to the direction of flow of electron. Apply the Fleming's left hand rule. Here, magnetic field, index finger this way, correct? Current from top to bottom, middle finger. So I have aligned forefinger or index finger for magnetic field, current, that is for middle finger, and therefore the thumb is pointing out of the board, that is towards you. It can be out of the page if I hold my textbook over here. In this case, option C is the correct answer. I hope you have understood these things. And there is one more numerical. Let me check what is that numerical. I think that numerical is there as a part of in-text question, which we will see this. Okay. Now we look into magnetism in medicine. I will read one paragraph from the textbook, which is very interesting and important. First of all, how this magnetism helps the medicine, or what is the application of magnetism in medicine? You must have observed the MRI scanning, which is also called magnetic resonance imaging. It is raining. Just a moment. Let me close the door. Yeah. You must have heard about magnetic resonance imaging. In our entire body, the nerve cells carry electrical impulse. The information is carried by the nervous system in the form of electrical impulses, and therefore the moving electrical charges or the current produces magnetic field in our body. Heart and the brain are the ones which produce maximum magnetic field. And therefore, magnetic resonance imaging is the technique by which the image of different body parts can be obtained on the screen, and thereby it can be studied. And this is the application of magnetism in the medicine. What do you think? If our body does not exhibit magnetism, then is it possible to use MRI scanning and all? Not possible. Because of the reason that the entire body behaves like a magnet, Because there is an electrical flow. Why there is an electrical flow? Because nerve impulses are transferred in the form of electrical impulses. When there is a flow of electrical charges, or when the electric current flows through the body, it behaves like a magnet. But what is the strength of this magnetic field? Body's magnetic field strength. If you check it, it is 1/1000th of the Earth's magnetic field, which is extremely extremely low. So the field strength of the body is very low. But of course, MRI scanning, as the heart and the brain produce maximum magnetic field, MRI scanning also can be used to study the heart parts and the brain parts, etc. Okay, this is one part. Now we'll look into next section, that is an electric motor. So what do you think is an electric motor, and what is the principle behind that, and what is the construction and working? In an electric motor, we are going to study what is an electric motor, the definition of an electric motor, that is, then what is that it is called DC motor. We are studying DC motor only. So what is the DC motor, and what is the principle of working, and what is the construction? These are the things which we are going to study. Okay, so let me direct it to the PPT for making few notes, and then I'll go to discuss on electric motor. Dear students, we'll have a look at one video clipping where practically this experiment has been performed. A current carrying conductor, when placed in a magnetic field, gets displaced. We'll see that video, and then we'll go to the motor part. What is a motor, and how the DC motor functions. Okay, first let us watch one video on this experiment.
So I have here a large magnet, south pole, north pole, so the field is pointing up. And then I have a big, copper tube, which is connected to the wire. So I have here a large magnet, south pole, north pole, so the field is pointing up. And then I have a big, copper tube, which is connected to the wires here and there. When I connect these here, electricity will flow through this guy, through the red, through the copper tube, and then up through ground, and then back home. So we'll have electricity flowing this way, magnetic field pointing up. We expect a force inward. And sure enough, we get an inward force. Now, if I reverse the direction of the current, we expect an outward force. Get this guy out of the way. You see it floating there, because now that I've reversed the direction of the current is flowing this way, magnetic field is pointing up, we expect an outward force. And that's what you see. Right hand rule simplified.
I think this experiment was quite clear. The motion of the conductors we could observe very clearly inside and outside the horseshoe mouth, horseshoe magnet. Okay, fine. I think we'll go to now. We were discussing about electric motor. What is an electric motor? We use electrical motors in our washing machines, in our fans, etc. The moment you switch on, fan will rotate. The moment you switch on washing machine, the drum starts rotating. That means motor can be said to be a rotating device in which electrical energy is converted into a mechanical energy. When we switch on the fan, we get air, isn't it? So basically an electrical energy is getting converted into a mechanical energy. Similarly in washing machines also. So what are the applications of electric motors? Where do you use? Electric fans, refrigerators, mixers, washing machines, computers, MP3 players, etc. Electrical energy is getting converted into mechanical energy, and therefore electric motor is a rotating device. You should keep it in mind. What is a DC motor? It is a motor in which the source energy is a direct current. There are two types of currents, AC and DC. AC is an alternating current which we find in our all household applications, and direct current is provided by a cell or a battery. What is the principle of a DC motor? So far whichever we experiment to observed, that is the basis for the working of a DC motor. So a current carrying conductor when placed in a magnetic field experiences a force and thereby the displacement is the principle of DC motor. So a DC motor works on the principle that a current carrying conductor when placed in a magnetic field experiences a force and thereby motion. So next is the construction part, construction and working part. See, for which I have a diagram something like this, and this diagram I would like to explain it on the board. The different components we'll see, and then the working also I'll explain on the board, and then you'll be directed to the PPT for making the notes. These are the two diagrams which have been drawn here about the motor. Motor is a rotating device that converts electrical energy into mechanical energy, and DC motor is the device in which the source energy is the direct current. What are the components we'll study first here in this motor? See, north, N and S, north and south, these are the permanent magnets, or of course we can use the electromagnets also, which are much more powerful. N and S, north pole and south pole, are the two permanent magnets. A, B, C, D is a rectangular coil which is placed inside the magnetic field. The ends of the coil A, B, C, D are connected to a split ring commutator. Here P and Q, shall I name it over here, N and S, here I will mention it, NS magnets. Permanent magnets. ABCD is a rectangular coil. P and Q are split ring commutators. Split ring commutators P and Q. These are called split ring commutators. And X and Y carbon brushes. Which are conductors. These are the main components. So what is this P and Q? We should know here what is this P and Q. P and Q are something like the cylindrical hollow bushes which have been cut into the central part, that is split into two parts, something like this. something like this. This is one half and another half will be this is another half. These are the two halves, small bushes. These are made up of copper and inside it is insulated. Inside portion it is insulated. This portion is insulated and outside it is conductive. That means the outer portion is conductive, the inside portion is insulated, and these X and Y are the two carbon brushes which are pressed against the conductive surfaces of the split ring commutator, and a battery terminals are connected to XY carbon brushes. Carbon brushes are used because they will be able to conduct the electrical current, and P and Q are the split ring commutator. What is commutator? Commutator is a device that reverses the direction of current in an armature coil or a rectangular coil ABCD. Okay, so what is armature coil? We'll see that later. But split ring commutators, why it is called a split ring commutator? Because it is split at the center over here. That means it is cut into two halves, left half and right half, and therefore these are these things which I have shown here. These are copper split ring commutators. The name split ring because the copper bush, hollow bush, is split into two halves. So what are the parts here? Permanent magnets, rectangular coil, P and Q split ring commutator that reverses the direction of current in the ABCD coil, and XY are carbon brushes. These carbon brushes are pressed against the external conductive surfaces of the split ring commutator by means of the springs, so that it establishes all the time contact with the split ring. So what is the function? How does it function? Let us start with see, there are two parts here. In this is the beginning of the cycle. Beginning of cycle, and here this is at half cycle. At half the rotation. At half cycle means at half the rotation, I'll say. At half the rotation. Okay. And one more thing here. This part which is the split ring commutators are placed on an axle. What is an axle? This is a central axis for which we can connect it to, a fan or a washing machine or something like that. So this is the axis. Okay, here we can connect it. Axle is at the center. This part is called axle. Axle is a piece of shaft, like something like this, on which the split rings are mounted. So inside the split ring, those are insulated ones, and external surfaces are conductive. This is the beginning of the cycle diagram, and this is after half rotation. At the half rotation, that means beginning of the second half cycle. There are two cycles. This is the first half cycle and this is the next half cycle also, I can say. So how does it function? Let us see. Already this is switched on. Now we'll apply the Fleming's left hand rule to arm AB and arm CD of this armature coil, or simply a rectangular coil. Armature coil is number of such rectangular coils which are placed one over the other, that forms an armature coils. And therefore sometimes if I say armature coil or a rectangular coil, both need to be considered to be same over here. Okay, let us start this now. Let us switch on. The current flows from positive terminal to the carbon brush X. It comes to arm AB. Direction of the current is from A to B. Direction of the current is from A to B, and then from B to C, and then from C to D here in arm CD. This is the direction, and comes back to carbon brush Y, and then the circuit gets completed. So in arm AB and arm CD, these are the directions of the current which have been marked. What about the direction of the magnetic field? Direction of the magnetic field is this way, from north to south. So direction of the field is from north to south. That I'll mention here. Here. This is north to south. By applying Fleming's left hand rule for arm AB, let us try to understand in which way arm AB will get displaced. Now let us take Fleming's left hand rule. With this I can make use of, so that explanation also is very clear. Now field north to south, point this way. The index finger gives north to south the direction of the magnetic field. Current from A to B, this is here plus here and this is minus. So current is from A to B. That means the current should be something like this. This is the middle finger. This is the field, the current this way, and therefore this thumb points the direction of the arm AB here. Arm AB moves into the board now. Do you understand? Into the board. This is how it is. This is the direction of the magnetic field. This is the direction of the current, and arm moves this way, or I will say arm moves downward now. Arm moves downward. So like this, N to S, index finger, current this way, current is MFC, current is this way, okay, yeah, this way, exactly. Field, current, and thumb gives you the inward into the board, or this is being a three-dimensional, I'll say downwards, and therefore the force experienced by this conductor, here it is into the board or downwards, something like this. Now let us apply the Fleming's left hand rule for this arm. Same time, at the same time we'll apply here. North to south field, north to south field, north to south field. Current is from C to D. Here, see here, north to south, and current is from C to D. This arm experiences a force, thumb, which is towards you out of the board, and therefore upwards. And therefore this experiences the upward force. Meaning in this three-dimensional figure, by applying Fleming's left hand rule to arm AB, AB moves downward and this arm CD moves upward. So this force, this is F here and this is F over here. Two equal and opposite forces with different point of actions or the different lines of actions on the same object over here behave like a couple, and that couple leads to the rotation of this armature coil or the rectangular coil ABCD. So if this is the coil here, if this arm moves up, this arm goes down. In this way, the rotation of the rectangular coil takes place. This is what I'll mark like this. Is it clear for all of you? Now certain changes I'll write over here, and that I'll compare with that diagram. First of all, I'll write here, I hope it is clear. Direction of the current, one is current direction and force direction. In arm AB, current from A to B, and force downward. Okay. Now in arm CD, the current is from C to D, and force upward. These two forces are mutually parallel to each other, equal and opposite, and therefore act like a couple. The couple acts on an object to create a rotational effect, and therefore this armature coil, it rotates like this. So after a half cycle, this arm comes this side, arm CD comes this side, which is represented in this diagram. Now come to this diagram. Now what happens, let us see once again. Here important is P and Q are the split ring commutators. that are permanently fixed to the axle, and therefore along with the axle it has rotated, the armature coil has rotated, but X and Y are the carbon brushes which cannot rotate. Remember, X and Y carbon brushes cannot rotate, whereas the split ring commutator rotates. So this has turned it to half rotation. Arm CD has come this side, arm AB has gone this side. This is how CD and AB, the next position. So at first half cycle, this is the position. Check the split ring commutators P and Q. It is Q and P here because the PQ also split ring commutators are permanently attached to the ends of the rectangular coil. As the coil rotates, P and Q, the split ring commutator also rotates. Now P was in touch with X and Q was in touch with Y. After half rotation, Q is in touch with X and P is in touch with Y. This is the situation. Let us apply once again the Fleming's left hand rule for arm CD and for arm AB and check the rotation. Here, positive terminal current flows from this way and then to the brush X, split ring commutator Q, this way from D to C, from B to A, then split ring commutator P, carbon brush Y, then circuit gets completed. Let us apply. What about the direction of the magnetic field? North to south. Same. Here, this is this way. This is this way. Apply Fleming's left hand rule. Direction of the field this way. Field. Current direction from D to C. That means like this. D to C, this is the middle finger, from D to C, field this way, and this is D to C. In that case, the thumb is inwards. That means arm CD moves inward, or I will say the force here is downwards. Again, once again, the force is downwards. Let us apply simultaneously the Fleming's left hand rule for arm AB. Magnetic field, current B to A, something like this. This is the middle finger, B to A, field this way, and the thumb is pointing towards you. That means arm AB is coming upward. So this is the upward force. This is the upward force. Meaning, here also arm DC is moving downwards, arm AB is coming outwards. That means it is once again rotating in the same direction as the first case. This way, the rotation. That means the moment it takes a rotation, AB comes back to the initial position, CD goes back to the initial position, and once again this cycle continues. First half cycle, this arm comes to this side and this arm comes to this side. Next half cycle, it achieves its original positions. So this is the first half cycle, which is called the beginning cycle, and this is the next half cycle. In both the cases, check the direction of rotation. It is in the same direction, and hence this starts rotating in anti-clockwise direction. You got it? In anti-clockwise direction. Now let me write these things, these parameters I and F in this case. The current in this case and the force in this case. AB, CD, and force also. Now check here. In AB, current flows from B to A. From B to A. In CD, current flows from D to C. D to C. Force experienced in arm CD is downward. And this is upward. Upward. Why I am comparing? Very important comparison. Arm AB, first case, second case I am comparing now. Arm AB, current flows from A to B in the beginning. Now it is from B to A. arm CD, current flows from C to D in the beginning. It is D to C. That means the current in arm AB and CD got reversed. Is it clear from this one? The current got reversed, and therefore what is that is how it is getting reversed? Because the split ring commutator is responsible for changing the direction of the current here. What about the forces? Earlier case, first beginning of the cycle, arm AB experienced downward force, but in the second case, arm AB experienced downward force. Arm AB here, I think I have made a mistake here. Yeah, arm AB upward. Just a moment. AB is upward, and arm CD D to C, it is downward. Okay. Okay, fine. So let us compare now the forces. Arm AB downward in the beginning, arm AB upward. Arm AB downward in the beginning, arm AB upward here, downward here, upward here. As the direction of the current changes, the direction of the force got reversed. A to B, the flow of current, downward force. B to A, the flow of current, upward is the force. Similarly, in arm CD, C to D was the flow of current, upward force. Now D to C, current, force downwards, and therefore in both the arms in one cycle the current changes its direction and the force also changes, but overall if you look at the total rotation of the armature coil or the rectangular coil is only in one direction. I hope you are able to understand, and therefore this will start rotating in only one direction continuously. So for this axle I can connect a fan which will give the air, or for this axle which is nothing but the shaft, which we can connect it to the washing machine which would be able to wash. So the rotating shaft here, the axle also rotates when the armature coil rotates along with PQ split ring commutator, and thus an electrical energy, if I switch on, the rotary action is obtained on the axle, and therefore this is a motor in which it is a rotating device and in which the electrical energy is converted into a mechanical energy. So I hope you have understood the construction part and working of the DC motor in the beginning of the cycle at the half rotation. So these two cycles are called first half cycle and next half cycle, put together one complete cycle. Important points have been highlighted here: how the direction of the current changes in the two arms and how the forces change in the two arms due to change in the current in due to change in the direction of the current. But overall, if you look at the direction of rotation of the coil remains same, and hence the DC motor rotates in only one direction. What else is to be discussed over here? Let me check now. First I'll check point by point and then we'll see. An electric motor is a rotating device that converts electrical energy into mechanical energy, correct? Electric motor is used as an important component in electric fans, refrigerators, mixers, washing machines, computers, MP3 players, etc. Okay. DC motor, the source is direct current. Principle: a current carrying conductor when placed in a magnetic field experiences a force and thereby deflection or the motion, and that is the principle. Construction: a rectangular coil ABCD of insulated copper wire is placed between the two magnetic poles, and such that arm AB, this arm AB and arm CD are perpendicular to the magnetic fields. The magnetic field is this way, the current is this way, so both are mutually perpendicular to each other. The ends of the oil are connected to, these two ends of the coil are connected to two halves of a split ring commutator P and Q. Inner sides of the split ring commutator are insulated and attached to the axle, inner side, and outer sides are, and the external conducting edges of the split ring commutator are to touch two conducting brushes which are called carbon brushes X and Y. Brushes are connected to external battery in this way along with the switch. This is about the construction. Let me read for you the working principle. working of a DC motor. When a battery is switched on, current in the coil flows along the path A, B, C, D. Yes, like this, along the path A, B, C, D. Thus, current flows in arm AB from A to B and arm CD in arm CD from C to D. That is in the beginning of the cycle. Applying Fleming's left-hand rule to arm AB and CD, we find that force on arm AB pushes it downwards while the force on arm CD pushes it upwards. Thus, the coil and the axle rotate in anti-clockwise direction. Is it clear? Okay. After completing the half rotation, at the half rotation or the beginning of the second cycle or the beginning of the second half cycle, at half rotation or the beginning of the next cycle or beginning of the second half cycle, the current in the coil gets reversed by the split ring commutator and flows along the path DCBA. Is it correct? Like this, X, Q, D, C, B, A, Y, P, Y and back. Yes, perfectly all right. Therefore, in the second half cycle, the current flows along the path DCBA. That's right. In arm CD, current flows from D to C, and in arm AB, current flows from B to A. Yes, correct. Applying Fleming's left-hand rule to arm CD and AB, we find that force on CD pushes it downwards, yes, and the force on AB pushes it upwards. And therefore, two mutually parallel, opposite forces with different lines of action set a couple. That couple rotates the armature coil or the rectangular coil ABCD in anti-clockwise direction. So the couple sets the coil in rotation. That is important. Okay. So that's how it is. Thus the coil and axle rotate in anti-clockwise direction. Once again here also. The split ring commutator reverses the direction of the current and has the forces acting on these arms. So very clearly here I have mentioned, according to that diagram and according to this diagram, how the change in direction of the current takes place in arm AB and CD and how the direction of the force takes place. So these are important observations which you must note down and understand. Thus, as long as the current flows, the coil rotates only in one direction continuously. This is how the DC motor works. We are going to see some small video clipping also how the DC motor works. Now, second point. One important point here, how to enhance power and speed of a motor. Very important. How to enhance power and speed of a motor. Listen carefully. Using electromagnets in place of a permanent magnet to increase the magnetic field strength. We can increase the power of the motor and the RPM. The RPM, what is RPM? It is the revolution per minute. RPM means revolutions per minute, which is the speed of the motor. It is my speed of the motor is measured in terms of RPM, revolutions per minute. So first thing, by increasing the pole strength or the magnetic field strength, by converting them to electromagnets instead of permanent magnets, we can increase the strength and thereby we can increase the power or the power of the motor. Second, by increasing the number of turns in the coil. ABCD, here it is a single turn. If we increase to many turns, then it becomes an armature coil. And therefore, how do you define an armature coil? Large number of turns of insulated copper wire wound on a soft iron core is called an armature. What is an armature? Large number of turns wound on a soft iron core, that is a rectangular iron core, is termed as an armature coil. So by increasing the number of turns, we can increase the power and speed of the motor. Third one, by increasing the area of the coil. See, ABCD, this is the area here. By increasing the area of the coil, so by increasing, how do you increase the area of the coil? There is a limitation. You cannot increase the area only of ABCD coil. Instead of that one, you go for many number of such rectangular armature coils. You know, there is one rectangular coil over here and you can have many number. Thereby the area also increases. So by increasing the area of the armature coil, we can increase the power and speed, and finally by increasing the current through the coil. The magnitude of the current if we increase, the speed and power increases. To once again summarize, power and speed of the motor can be increased by increasing the magnetic field strength. That is, we can go for electromagnets instead of permanent magnets. Of course, we can change the polarity also in that case. Second, by increasing the number of turns of the rectangular coil, that is by going for armature coil. Third, by increasing the area of the cross section of the armature coil. And for lastly, by increasing the magnitude of the current in the armature coil. So these are the methods by which we can increase the speed and the speed and the power of the motor. So that's all, students, with respect to the motor. Now you will be directed to the PPT. After that one, we'll watch a small video clipping on how this functions. Okay, so let us turn back to the PPT now. Yeah. Here, motor. What is DC motor? Principle, construction. Whatever I read, that was drawn on the diagram also. So pause the video and make a note of all this. Next, this is how it looks like. The same diagram was drawn on the board. Here you can see very clearly the split ring commutators. A hollow cylindrical copper bush which is split into two halves is called split ring commutator. One half this side, another half this side, and these two halves, externally these are conducting surfaces, internally these are insulated surfaces, and inside an axle is mounted, or the split ring commutators are fixed onto the axle. So if the coil rotates, then the P and Q split ring commutators will rotate and thereby lead to the rotation of the axle also. And the axle can be connected to like a fan or MP3 player or a washing machine. So these are the two diagrams you must note down. So beginning of the cycle at half rotation, that is the next half cycle. These are the changes which I have explained clearly. Pause the video and note down. And working of the motor after completion of the half rotation, how does it work and how to enhance and the power and speed of the motor. And this is how commercial motors work basically. And what is an armature coil finally over here. So before we end the lecture, we'll have a short clipping, a video clipping on how DC motor works, and then we'll end the lecture over here. Okay, fine students, I think let us pause a little bit till we open the video.
Fundamentals of a DC motor. Did you know the secret behind the mind-boggling speed of TGVs? One of the fastest trains in the world is the use of electric motors, not only in transport sector. Electric motors find their application in areas as diverse as household appliances, commercial complexes, in devices used for lifting and moving objects, and even in toys. Motors powered by direct current are referred to as DC motors. A simple DC motor consists of a rectangular loop P, Q, R, S, made of an insulated copper wire. This loop is placed in between two magnets such that the plane of the loop is parallel to the direction of the magnetic field. The ends of the loop are attached to the two halves X and Y of a split ring commutator. These halves of the split ring are insulated from each other and are mounted on an axle about which the rotation is to take place. Externally, two conducting stationary brushes, B1 and B2, keep pressing against X and Y respectively. These brushes are connected to a DC source. Let us now understand how this assembly works. Let the current from the battery enter through brush B1, flow through loop P, Q, R, S, and leave through brush B2. Here, the arms QR and SP do not experience any force, as they are either parallel or anti-parallel to the magnetic field. But the arms, PQ and RS, which are perpendicular to the magnetic field, experience a force each. The direction of this force can be determined using Fleming's left-hand rule. According to this rule, if the first finger points in the direction of the magnetic field and the second finger points in the direction of the current in the conductor, then the thumb points in the direction of the force exerted on the conductor. Applying this rule on arm RS, we find that the force acting on it pushes it upwards. Now, we move on to arm PQ to find the direction of the force acting on it. Here, we notice that the first finger points in the direction of the magnetic field, but the second finger does not point in the direction of current. So we rotate the left hand such that the second finger points in the direction of current. Notice that, in this case, the thumb points downwards. This implies that the force acting on arm PQ pushes it downwards. Thus, under the action of these two forces acting on arms PQ and RS, having different lines of action, the loop starts rotating anti-clockwise. Just as the rotation starts, arms QR and SP are no more parallel to the magnetic field, and hence are acted upon by the forces as well. But as the two forces are equal and opposite, and have the same line of action, they always cancel each other. Once the loop has rotated through 90 degrees, brushes B1 and B2 lose contact with the split ring and the current in the loop is cut off. In the absence of current, arms PQ and RS do not experience any force. This implies that the loop should not rotate anymore. However, due to rotational inertia, the loop continues to rotate a little further so that the contact is reestablished. Just as that happens, the current starts flowing in the loop once again, and the loop continues to rotate in the same anti-clockwise direction. On rotating through 180 degrees, that is, after half rotation, arms PQ and RS of the loop get interchanged. Now, the split ring Y is in contact with brush B1 and X with brush B2. Therefore, the direction of current flow in arm PQ gets reversed. This happens in arm RS as well. The reversal of current also reverses the direction of forces acting on them. Thus, arm PQ of the loop, which was earlier experiencing a downward force, now experiences an upward force. Likewise, RS experiences a downward force. As a result, the loop continues to rotate anti-clockwise. Again, when the loop has turned through an angle of 270 degrees, the brushes and the split ring lose contact. But due to rotational inertia, the loop continues to rotate a little further so that the contact is established once again. As soon as that happens, the current starts flowing, and due to the forces on arms PQ and RS, the loop continues to rotate until it completes one full rotation of 360 degrees. This whole process is repeated a large number of times so as to obtain continuous rotation of the loop. Rotational speed of the motor depends upon several factors. Notice how on increasing the number of turns of the coil, the rotational speed increases. On increasing the area of the coil, the speed further picks up. If the current is increased, the rotational speed mounts up further. Finally, if we increase the strength of the magnetic field also, the rotational speed will touch a new high. In order to achieve high power, a practical DC motor uses an armature coil consisting of a number of coils mounted on a soft iron core. This armature is located in between two or more electromagnets. On passing current through its coils, the armature starts rotating. The rotating armature turns the shaft to which it is attached. Thus, the electrical energy supplied by the source gets converted into mechanical energy. Summary. Motors powered by direct current are referred to as DC motors. Upon passing current through the loop, there is reversal of current after every half rotation, giving rise to a continuous rotation of the loop in the same direction. Rotational speed of the motor depends upon several factors, like the number of turns of the coil, the area of the coil, current in the coil, and the strength of the magnetic field.
Yes, students, I hope you have understood the functioning of DC motor. Very important two concepts today we studied. So we'll end the lecture over here and see you with the electromagnetic induction and Faraday's laws of induction in my next lecture, and that will be the last lecture for the conceptual part. After that one, question answer sessions will be there. Okay, so see you in the next lecture. Thank you for watching.